Okay, 6.3, proving quadrilaterals are parallelograms. In 6.2, we were told that a figure was a parallelogram, and we were able to deduce some of the properties of its parts. This is almost like the converse of what we did in 6.2. In this case, we're not given that it's a parallelogram. We're only given that the figure is a quadrilateral, but we want to use some of the parts to say if these parts hold certain properties, that the figure will be a parallelogram. And the first one we want to say is if the diagonals of a quadrilateral bisect each other, then the quadrilateral is a parallelogram. I'm going to prove this by showing that if the diagonals bisect each other, the top and the bottom will be parallel, and a similar argument would show that the left and the right would be parallel. What I'm going to do is I'm going to look at two triangles. The triangle on the top I'm going to call triangle 1. The triangle on the bottom I'm going to call triangle 2. Because the diagonals bisect each other, I already have two pairs of congruent parts, two sides. A quick inspection says I also have vertical angles. The vertical angles will be congruent, so the top triangle and the bottom triangle will be congruent by side angle side. If the triangles are congruent, their corresponding parts are congruent, so this angle must be congruent to this angle. Well, those angles are the insides of a Z. They are alternate interior angles, and the converse of the alternate interior angles theorem says if a transversal cuts two lines such that alternate interior angles are congruent, then the two lines must be parallel. And so by the converse of the alternate interior angles theorem, I know that the top line and the bottom line must be parallel, and it's a very similar proof to show that the left and the right must also be parallel. So if the diagonals of a quadrilateral bisect each other, then the quadrilateral is a parallelogram. Algebraically, I may ask this. It looks a lot like what we did in the last section, but there is a subtle difference. Now I'm going to ask, what value would x have to be in order for this figure to be a parallelogram? Well, in order for it to be a parallelogram, it is true that the diagonals would have to bisect each other. So I would say it must be the case that 2x plus 5 is equal to 5x minus 7. I'll add 7 to both sides. 2x plus 12 is equal to 5x. I'll subtract 2x from both sides. 12 is equal to 3x, so x is equal to 4. If x is not 4, this is not going to be a parallelogram because the diagonals will not bisect each other. If x is equal to 4, that actually in itself would not be enough proof to say it is. I would also have to make sure that the other diagonal was bisected also. Okay. Problem number 1, if the diagonals of a quadrilateral bisect each other, then the quadrilateral is a parallelogram. Property number 2, if both pairs of opposite sides of a quadrilateral are congruent, then the quadrilateral is a parallelogram. Okay. Notice it says both pairs. If you only have one pair, that is not enough information. I can prove this fairly easily also. The way I'll prove this is I will draw a diagonal. Cuts me into two triangles, triangle 1 and triangle 2. I already have, by the fact that the opposite sides are congruent, I already have two sides. By the reflexive property of congruence, I also now have the third side. These two triangles are congruent by side, side, side. Their alternate interior angles must also be congruent. If the alternate interior angles are congruent, then the lines must be parallel. I could use a similar proof to show that the left and right lines are parallel, and so it is true that if both pairs of opposite sides of a quadrilateral are congruent, then the quadrilateral is a parallelogram. I may ask a question something like this. What values do I need for x and y to ensure that this quadrilateral is a parallelogram? You wouldn't see the tick mark showing that they're already congruent, but that's what we would have to do. We would have to make sure that 5x plus 7 is equal to 2x minus 5, which would tell me that, I'm sorry, let's change this to 5x minus 7 and 2x plus 5 so I get something that actually works. Now I would say 5x minus 7 is equal to 2x plus 5, 3x is equal to 12, x is equal to 4. Solving for y, I'll do that in the middle of the parallelogram. y plus 3 is equal to 7 minus y, adding y to both sides. That's a plus. 2y plus 3 is equal to 7. Subtracting 3 from both sides, 2y is equal to 4. Y is equal to 2. So x would have to be 4. If x was 4, I would have 13 on the top and 13 on the bottom. Y would have to be equal to 2. I would have 5 on the left, 5 on the right. Opposite sides would be congruent. If the opposite sides of a quadrilateral are congruent, then the quadrilateral is a parallelogram. Number 3, if one pair of opposite sides of a quadrilateral is both congruent and parallel, then the quadrilateral is a parallelogram. Like before for my proof, I'm going to draw a diagonal. Once I drew the diagonal, I already have one pair of congruent sides. My diagonal will be congruent by the reflexive property. Notice this time I already have one parallel line. These lines are already parallel, so the alternate interior angles theorem will tell me that these two angles are congruent. Now that I know that those two angles are congruent, I know that the triangles themselves are congruent. Triangle 1 and 2 are congruent by side angle side. Okay, I already had one z. Now I can look at this other z, the one for these other angles, trying to get my lines parallel. So let's look at this z. Well, these two angles are corresponding parts of congruent triangles, therefore they must be congruent. Now by the converse of the alternate interior angles theorem, I know that this side must be parallel to this side. If that is the case, then the figure must be a parallelogram. How would I try to solve this algebraically? You can already see that the top line is parallel. Once again, I'm going to change this, I think, to a 2x plus 5, and I'm going to change this one to a 5x minus 7. What would the value of x have to be? Just like before, we would set these two equal to each other. We would find out that x has to be 4 in order for this to be a parallelogram. But if x is equal to 4, since the top is 13, the bottom is 13, the top and the bottom are both congruent and parallel, that would be enough to prove that that quadrilateral was a parallelogram. Number 4, if both pairs of opposite angles of a quadrilateral are congruent, then the quadrilateral is a parallelogram. Believe it or not, this is probably the easiest proof of all. We have the alternate of the same side interior angles theorem that says if same side interior angles are supplementary, then the two angles must be congruent. Well, I'm going to say that maybe the measure of this angle is x and this angle is y. Okay, if that's the case, then this has to be x and this has to be y. Well, I know that the sum of the measures of the interior angles of a quadrilateral is 360 degrees. So 2x plus 2y is equal to 360. Distributing out the 2 times x plus y is equal to 360. X plus y must be equal to 180 degrees. Well, if that's the case, this angle and this angle must be supplementary. Because they are supplementary, this side and this side must be parallel. Also, this angle and this angle are supplementary. Because they're supplementary, this side and this side must be parallel. So if both pairs of opposite angles of a quadrilateral are congruent, then the quadrilateral is a parallelogram. Okay, so once again, algebraically, I might say what value of x would you need in order for these to be a parallelogram? Here I'm going to put 2x plus 5. Here I'm going to put 5x minus 7. Solve this thing enough times to know that x would have to be equal to 4. Okay. That being said, this in itself is not enough information to show that it's a parallelogram. It has to be true that x is equal to 4, but in order to prove it's a parallelogram, I would have had to show that both pairs of opposite angles are congruent, so I would have had to have some way to show that these opposite angles were also congruent. That's the only way I would be able to say that the quadrilateral is a parallelogram. However, if x was not equal to 4, there would be no way that this could be a parallelogram because these two sides would not be congruent. I couldn't use this as a proof. All right, so here comes practice number 1. Solve for the values of x and y needed to make the figure be a parallelogram. Like before, I know one of the things that we need to figure out is that how we're going to make these things be parallel. Well, clearly this and this, in order to be, because they are same side interior angles, they would have to be supplementary for the lines, the top line and the bottom line, to be parallel. I would have to say that 8x plus 3 is equal to 8x plus 3 plus 2x plus 7 would have to be equal to 180 degrees. Combining like terms, 10x plus 10 is equal to 180. So 10x must be equal to 170 degrees. So x must be equal to 17. Okay, I know it looks an awful lot like what we did in section 6.2, but before we knew it was a parallelogram and we asked what the measures would be. In this case, it's just a little bit different. We said, okay, what would the values have to be in order to make this thing be a parallelogram? And the answer is x would have to be 17. Okay. If x is equal to 17, 2 times 17 plus 7 is going to be equal to 41. Well, if this is going to be a parallelogram, opposite angles would have to be congruent, and so y minus 6 would have to be equal to 41. Y is equal to 47. So x would have to be equal to 17. Y would have to be equal to 47. Okay, practice number 2. All right, solve for x and y that will make the figure be a parallelogram. I forgot to tell you to pause last time. Hopefully you did. Go ahead and pause and see if you can solve these on your own. Okay, the easy one to solve for here is going to be x. In order for this to be a parallelogram, the top and the bottom would have to be congruent. 6x plus 4 is equal to 8x plus 3. Subtracting 3 from both sides, 6x plus 1 is equal to 8x. Subtracting 6x from both sides, 1 is equal to 2x. Dividing both sides by 2, x is going to be equal to 1/2. Let me check that. 6 times 1/2 is 3. 3 plus 4 is equal to 7. Down on the bottom, 8 times 1/2 is 4. 4 plus 3 is equal to 7. X has to be equal to 1/2. Solving for y, the two sides left and right would also have to be congruent, so we would say y squared, let's try that again, y squared is equal to 3 minus 2y. Because this is a quadratic, I'm going to put it all on one side. Okay, so I'm going to add 2y and subtract 3, and I will get y squared plus 2y minus 3 is equal to 0. I need two numbers that multiply to give me negative 3 and add together to give me 2. Okay, the two numbers that multiply together to give me negative 3 and add together to give me 2 are 3 and negative 1. 3 times negative 1 is negative 3. 3 plus negative 1 is 2. So I can factor this equation as y plus 3 times y minus 1 is equal to 0. Well, if a product is equal to 0, one or the other factors has to be equal to 0. So y is equal to negative 3 or y is equal to 1. If I try negative 3 on the left, negative 3 times negative 3 is 9. If I try negative 3 on the right, negative 2 times negative 3 is 6, so I get 3 plus 6 is equal to 9. Negative 3 is a good solution. If I try 1 on the left, 1 squared is 1. If I try 1 on the right, 2 times 1 is 2. 3 minus 2 is equal to 1. 1 is a good solution also. So my value of x would have to be 1/2. My value for y would be negative 3 or positive 1. All right, practice number 3. Solve for the value of x and y that will make the figure a parallelogram. Pause your computer and let's see if we can solve this one. Okay, in order to solve for x, these two angles would have to, these two sides would have to be congruent. So 2x plus 3 is equal to 4x minus 1. Adding 1 to both sides, 2x plus 4 is equal to 4x. Subtracting 2x from both sides, 4 is equal to 2x. X must be equal to 2. If x is equal to 2, this side would be 7, this side would be 7, and so it looks like this would be a midpoint, and so this segment here bisected the segment we were looking for. We also need to set y minus 10 equal to 18 minus y. I'm going to add y to both sides. 2y minus 10 is equal to 18. I'm going to add 10 to both sides. 2y is equal to 28. Y is equal to 14. 14 minus 10 is 4. 18 minus 14 is 4. Both of those segments would be 4. They would be congruent. So this segment also bisected this segment. Both segments bisect each other. That is enough to say that the figure is a parallelogram. Practice number 4. Quadrilateral has vertices at 0, 0, 2, 4, 6, 3, and 8, 7. We need to prove that ABCD is a parallelogram by showing one pair of opposite sides is congruent and parallel. Pause and see if you can solve this by yourself. Okay, hopefully you were able to do this, but if not, if I want to show opposite sides are congruent and parallel, I think I'll do the top and the bottom side. Okay, and I think I'll do the easy part first, which is to show that they're parallel. Well, the thing I know about parallel lines is that they have the same slope, and conversely, if two lines have the same slope, they're parallel. Okay, what's the slope of the top line? Well, I go up 1, 2, 3, and I go over 1, 2, 3, 4, 5, 6. Okay, so I've now got a right triangle. One leg is 3 and one leg is 6. Pythagorean theorem tells me 3 squared plus 6 squared is equal to what I'm looking for squared. 9 plus 36 is x squared. 45 is equal to x squared. X squared is equal to the square root of 45. And for the purpose of proving, we could let it be equal to the square root of 45, but I'm going to go ahead and simplify that as 3 times the square root of 5. Okay. Wow, look, I did both things. Okay. By the way, that is not the slope. The slope is going to be over here. It's going to be 3 over 6, which is 1/2. So I gave you a slope here of 1/2, and the length of the segment is 3 times the square root of 5. Looking at the bottom side, oh look, I've got a rise of 3. I've got a run of 6. The slope for the bottom is also 3, 6, which is 1/2. Oh, the two lines are parallel. They have the same slope. Also, I've got another right triangle whose legs are 3 and 6. 3 squared plus 6 squared is equal to x squared. X must be equal to 3 times the square root of 5. Since the lines are parallel and congruent, that is enough to show that ABCD is a parallelogram. Practice number 5. I want to show that the same figure is a parallelogram, this time not by the fact that the one pair of opposite sides is congruent and parallel, but by the fact that the diagonals bisect each other. This also looks like it may be hard, but it's not easy if you'll just find the midpoints of both the segments. So pause your recorder and try to do that. Okay, here we go. I'm going to draw the first diagonal. And I want to know what's the midpoint, because if I'm bisecting this segment that's a diagonal, I need to know what the midpoint is. Well, the x values are 0 and 8. Halfway between 0 and 8 is 4. Okay. The y values are 0 and 7. Halfway between 0 and 7 is 3.5. So the midpoint of this diagonal is 4, 3.5. Now I'm going to draw this diagonal. I want to find the midpoint of this diagonal. Well, the x values are 2 and 6. Halfway between 2 and 6 is 4. 4 and 3 are my y values. Halfway between 4 and 3 is 3.5. The midpoint of the green diagonal is also 4, 3.5. 4, 3.5 belongs to both of the diagonals. It's a point on both the diagonals. And so where these intersect, notice that these two must be congruent because 4, 3.5 is a midpoint. These two must be congruent because 4, 3.5 is a midpoint. They bisected each other. If the diagonals bisect each other, then the figure is a parallelogram. Okay? I don't have to do any more work than that because the midpoints of both the diagonals were the exact same point. Those two diagonals bisect each other. That's enough to say this is a parallelogram. Okay? Hopefully this has helped you with some of the things that you want to do, and I'm sure we will do more in class.